Hi, this is Annie Powell, and I will be talking about my Lab 2 for Physics 2211. For the introduction, the purpose of this lab is to compare computational and observed models of projectile motion, taking drag force into account. The big idea is projectile motion, so we will be tossing a ball to analyze the motion. What is terminal velocity? This is a big term for this lab. This occurs when freely falling objects have zero net force. And how is it connected to drag force? The gravitational force is balanced by drag force, making net force equal to zero. And then what is the drag force? Essentially, friction or resistance experienced when an object moves through a fluid such as air. So that applies to this experiment because we're tossing an object and it's going to experience drag force from the air. Some key equations. We have our position update, velocity update, and average velocity. These were used last time, but they apply for both just kinematics and projectile motion. Some assumptions are that drag force is proportional to velocity squared, acceleration due to gravity is constant, and it's always going to be negative 9.81 meters per second squared. And then for our systems and surroundings, the system is the ball and the surroundings is the air, which is causing the drag force. We can see here, this is a picture of the analysis and tracker. So we took a ball, we tossed it, we had two measuring sticks pointing up and one pointing on the bottom so that we could analyze the motion from both directions, even though we only ended up using the Y in the end. And then here's where the ball was released from the hand. The ball is at the bottom in this image, but it was released from the hand, and you can see the arc in tracker. Right. For our computational model, calculations for Y, this is what it looked like. So we had the gravitational force and then the drag force and then F net, which is going to be the gravitational and the drag force summed. And then we defined the ball's velocity. So this is just going to be based on our kinematics equations before, and same for the position. So this is going to be the velocity update and the position update here. And then for velocity versus time models, so we have one model with drag and one without drag. The without drag, we're just going to make B equals 0. That's going to be the drag force. And then with drag, it was actually 0.002, but this is just an example of changing the drag force. So I kind of messed with that for a while to see when it was closest to our actual data to find a good drag force. And the primary difference is just changing the drag force to be a little bit higher to indicate that there was some resistance in the air against the ball. Output of the code, so for no drag force, this is what the chart looked like, and you can see the data starting at the bottom. I have some more graphs of this later, but this is just an example of the output. And then for the drag force equaling 0.002, this is what it looked like. So you can see it's very steep drop off and a lot more steady along the top. So that's a main difference. With it's no drag force, it's kind of like a little bit more of a constant slope, and then with the drag force, it's a much more sudden slope down. Predicted versus observed data. I couldn't seem to get these both on the same chart, but for drag versus no drag of the predicted data, we can see that with the drag force, it's going to be a lot more like flat, constant line, and then with no drag, it's going to be much more sloping downward, and this is going to be time versus position. And then for the observed data, it's a little bit more of an arc. And yeah, if the object were thrown straight up, it would have, and in this case, it's going to have the same initial speed as in the experiment. It would take longer to reach the ground because it experiences an upward force rather than minimal upward force from the horizontal toss like in the lab. So the gravitational acceleration is the same in both cases, but the upward force opposes gravity more. Some potential errors: imperfect measuring technique in the tracker analysis, incorrect drag force prediction, slight force from the hand tossing the ball causing horizontal acceleration. And in conclusion, including drag force and calculations for predicted projectile motion will make data more accurate because it opposes the gravitational forces and makes F net 0. Right? Thank you for listening.